In this section of chapter 19, I will discuss about laws of thermodynamics and types of randomness. First law of thermodynamics tells us that energy is conserved. You can neither create energy nor destroy energy. You can change energy from one form to another form. Second law of thermodynamics tells us that spontaneous processes take place only in one direction and are irreversible. Think about in fall, leaves come down, but the same leaves cannot go up spontaneously. And this is a spontaneous process which happens in only one direction. That means it falls downward. Now, why it falls downward? We're not looking for the reason, but all of you know that because of the gravity, it falls downward. The second way of defining second law of thermodynamics is, in a spontaneous process, entropy or randomness of the universe is increased. So I'm going to define you what entropy or randomness is. But before that, I'm just giving you the definitions. For system, change in entropy or randomness of the system plus change in entropy of the surroundings would be greater than zero. That means, you know from calculus that change greater than zero or positive means final is greater than initial. So that final randomness would always be greater. That means in natural process overall randomness is increased. Now what is system? Let me define here system so that we can understand it. Say you are doing a reaction in a container, in a beaker for example. Your focus would be what is happening within the beaker, and that's the system. Everything else outside of the beaker would be surroundings. So that's why we define here everything outside of the system is surroundings, and system means portion of the universe where we focus our attention. Now the third law of thermodynamics, entropy or randomness of a pure crystalline substance at 0 degree Kelvin is zero. Now here we're going to discuss types of randomness, and we'll begin with translational randomness. As an example, I have picked carbon dioxide, CO2. Now there could be several different types of motion possible, and that motion obviously would contribute to randomness. For example, this carbon can move from left to the right, and that's translational. So how do I define translational? If you think about center of mass is somewhere here along this line. Center of mass is going to move from here, from left hand side to the right hand side, so new center of mass would be here. So this is a translational motion where center of mass moves from one location to another. Say you are jogging or you're walking, your center of mass would be somewhere in the middle of your body, and that moves when you're jogging or you're walking, and that's translational randomness. Now rotational randomness. Again, first I'm going to show you with carbon dioxide. Carbon dioxide, where position of the carbon may remain intact, but still there could be some movement. Oxygen can go from left hand side towards that axis, and other oxygen can also move along the direction of the arrow. So that could be a rotational motion. Same thing can be said about yourself. If you rotate, you don't have to change the location of your center of mass. So in rotation, center of mass does not move. Same would be the case with vibration. In this slide, we're going to discuss vibrational motion and vibrational randomness. We'll begin with the stretching vibration of carbon dioxide, the top molecule. Oxygen can go away from carbon, and that can happen on both sides at the same time, so that the location of center of mass does not change. This is called a stretching motion. You can have bending motion, where oxygen, in this case, will be bent away from carbon. This oxygen would also be bent away from carbon. But then carbon, in order to maintain its center of mass fixed, it has to move up so that center of mass remains in same location. So in the bottom figure, we can see that oxygens are moving upward, carbon has to move downward. So what we learn here is in only translational motion center of mass changes its position, but in rotation and vibration center of mass doesn't change its location or position. Now with that in mind, let's try to do this following problem. Identify the types of randomness in gaseous helium, hydrogen, solid ice, and liquid water. Helium is a noble gas. It remains as isolated atom. Does it have any translational motion? Yes, in the gas phase it can really move back and forth and it can go anywhere. And the center of mass would change its location, so that's why its translational motion is quite possible. Question is, can it have rotational and vibrational degree of freedom? Answer is no, because helium is not bonded to another atom to have rotational or vibrational motion. What about hydrogen molecule, H2? Two hydrogens are bonded. In the gas phase, it can have translational motion where the two hydrogen can move together. So the center of mass is going to move from this location to a new location. That's translational motion. Can it rotate? Yes, it can rotate like this. Again, the position of center of mass is not going to change. Can it vibrate? Yes, it can. It can vibrate like this. Two hydrogens would be going away from each other, and then all it can even come closer to each other. So H2 molecule can have, in the gas phase, can have translational, rotational, as well as vibrational degree of freedom or randomness. In case of solid ice, situation is quite different. In ice, you'd have water molecules bonded back to back, like you have a hydrogen acting as a hydrogen bond. I'm just showing you one such bond, but there are many such bonds in both liquid and solid. The difference is, in case of solid, they are held very rigidly. So when you have a rigid bonding in a solid, obviously you cannot have a translational motion. You cannot have a rotational motion. Only vibrational motion is possible for any solid. On the other hand, in case of liquid water, there is more degree of freedom. That's why water flows. And in case of liquid water, you'd expect some movement or translational motion. But it's not as free as in case of gas molecules, but it's still much freer than much free considering the solid molecules. In case of solid, they can't move away from each other. So in liquid, translational motion is possible. Rotational motion is also possible because, again, for the weaker bonding, and vibration is of course possible. Now here we're showing you how randomness may change with volume or space. So this gentleman is confined in a room. So I can specifically identify the location of this gentleman. I can say that, okay, the gentleman is in this particular room, so we can track him down quite easily. If I say that this gentleman is somewhere in State College or in Dubai, then you are not that specific anymore because the volume has increased. This gentleman could be anywhere in State College or in Dubai. So in other words, he has a greater randomness here. He can go anywhere. Now if I said that this gentleman could be anywhere in Pennsylvania, randomness would even increase more, because now this gentleman could be anywhere within the state Pennsylvania. So what we learn here is randomness changes with the volume. As you have increased volume, there will be greater randomness. So that means this gentleman can be anywhere within that volume. Now next, think about change in randomness with number when keeping the volume fixed. So say I have this is the room. Initially I had only one person. Later on there were 10 people there. Later on there were 20 people there. If I want to track down one person and say they all look alike, all those 10 people look alike, all 20 people, maybe one of them look a little different, but if I have multiple of the similar looking people, it would be impossible to locate when the number is increased. In other words, randomness is increased as number is increased. It would be much harder. If there is only one person, then you can track down that gentleman is sitting or waiting in that room. But if I have 10 of them, then it's harder to track down one person. If I have 20 of them, it will be much harder. So in other words, randomness increases with number. Randomness also increases with volume or space. Here there are specific examples with gas molecule on the left hand side. Now there is a valve. This is closed at this time. When you open it, you allow these gas molecules to go from one container to the other container. So they are going to go. That's the nature of the gas molecules, because they move at random. Whenever it finds opening, it would go from one container to the other. So even though this was vacuum to begin with, later on this will be all filled with gas molecules. And question is, can it go backward spontaneously so that you'd have vacuum back and all the gas molecules in one container? Answer is no. That's not going to happen spontaneously. So reverse process would not happen spontaneously, but the forward process where gas molecule expanded into the vacuum, that happened spontaneously. Now the question is, any change in randomness or entropy? Randomness is also labeled as entropy in this particular chapter. So it's the scientific name given to randomness. The question is there any change of randomness when gas molecules initially confined in one container, at the end it filled two containers? Yes, entropy is increased here because the volume is increased. Remember I gave you an analogy in last slide that as volume is increased or space is increased, there are more ways that gas molecules can move. And I gave you an analogy with human being, but that same is true for gas molecules. You can consider gas molecules to be human being, and as the number is increased, randomness is increased, or as the volume space increased, randomness is also increased, or in terms of entropy is increased. Now we are showing you another process. On the left hand side, we're looking at a beaker of water with sugar sitting at the bottom. You just added sugar, but you know that sugar is highly soluble. In a short amount of time, sugar goes in water solution, so you get a solution of sugar, and that happens spontaneously. Question is, would the reverse process happen spontaneously at the same temperature? No. Basically, you cannot have pure water on the top and sugar, solid sugar sitting at the bottom. You cannot go backward. So here also, reverse process is not going to happen spontaneously. So let's cross it out. Now, what kind of change had happened to randomness? Obviously, it has increased. Why it has increased? Initially, sugar molecule was confined to the bottom, so it has very little randomness. When it went in water solution, now it has the randomness throughout the volume of water. And that's why randomness is increased in this process. In this slide, we're showing you how entropy changes as the reaction happens. In first reaction, you have 2 moles of SO2 reacting with 1 mole of oxygen, forming 2 moles of SO3. So basically you begin with 3 moles and you end up with 2 moles. So what is happening? Number is going to decrease as products are being formed. Remember relationship we discussed with number and randomness. As number is decreased within the same volume, randomness is decreased. That means you can better track down any object. So randomness is decreased, so delta S has to be negative. Now, if you're a little bit confused about delta S, increase or decrease, how do you define that? Let's write down an expression for delta S. So delta S is given by randomness final minus randomness initial. When number is decreased, obviously final value would be smaller than initial value. Think about any number. Say final value is 5. And of course it has to be smaller, so initial is 10. So I'm getting 5 minus 10 is minus 5, so I get a minus value. So that's what we're showing you here. Delta is less than 0 or negative when it's decreasing. Let's try the second reaction. Barium hydroxide solid gives barium oxide solid and water vapor, water as a gas. What happens to randomness? So you begin with solid barium hydroxide. You know that solid doesn't have much randomness, only you know that vibrational randomness is possible. And barium oxide is also solid, having only vibrational degree of freedom. But on the other hand, gas has lots of degree of freedom because it can move to any volume and fill that whole volume. Since in gas phase you have all kinds of randomness, translational, rotational, vibrational, and of course it also fills the whole space of a container. So obviously randomness is significantly increased as you go from solid barium hydroxide to water vapor or water gas. So in this case, delta S has to be greater than 0 or positive. Let me explain problem number 43, and I would like to go over 2 problems, A and D. And A should be pretty straightforward to you because we have discussed similar problem. So let me show you for A, N2 gas reacting with 3 moles of hydrogen gas. These are all gases, giving 2 ammonia, 2 moles of ammonia gas. The question is delta S is going to be positive, negative, or no change? Delta S means final randomness minus initial randomness. Let's look at how they're different. I have 1 N2 and 3 H2. So I have 4 molecules. When it reacts, I end up with 2 molecules or 2 moles of product. So each time this reaction happens, the number decreases from 4 to 2. So that means randomness is decreased. So delta S is going to be less than 0 or negative. So I hope you understand that, because final value would be smaller, or you can think it, if you can better think it, delta S is final randomness minus initial randomness. Final value is smaller because I have a smaller number of molecules at the end, and initial value is larger. Now let's do part D, 43. Let me use a different color. Al2O3 solid reacting with 3 moles of hydrogen gas and giving 2 moles of aluminum solid and 3 moles of H2O gas. So the question is, what would be the entropy change here, sign of entropy change? Is it going to be positive, negative? Basically, they're asking for, is entropy increased or decreased or remain the same? Of course, we are dealing with 2 solids here on both reactant side as well as product side. And solid doesn't contribute much to randomness because they're confined within a small volume of the solid. On the other hand, gas can fill in any container. But the thing is, we have now gas on both sides. Not only that, their numbers are same. 3 moles on the left side, 3 moles on the right side. So number-wise, it's not changing. So normally you'd think when number is not changing, randomness would remain unchanged. That would be the case if we had the same kind of molecule on both ends. Here I have H2. Let me show you that how H2 would behave differently than H2O. That would make the subtle difference. This is H2, and let me show you H2O. Both are in gas phases, would have both translational, rotational, and vibrational motion. However, there is a difference in their vibrational motion, the types of vibrational motion. In case of hydrogen, H2, only stretching is possible. In case of H2O, we have a stretching motion, 2 hydrogens stretched out, and oxygen is going upward to conserve its location of center of mass. So that's stretching. So stretching is also possible. In addition to stretching, H2O, hydrogen can undergo what we call bending motion. Hydrogen gets this way, and oxygen has to move this way. That's the bending motion, and it's not possible in case of H2 because there are only 2 atoms bonded. You need to have at least more than 2 atoms bonded in order to have bending vibration like this. So because of the more ways that H2O molecules can vibrate, that's why randomness is going to be greater for H2O molecule than H2, and that's going to make the final difference. So as you go from 3 moles of H2 to 3 moles of H2O, you can say change in randomness will be small, but since H2O can undergo different degrees of randomness, especially due to its bending vibrations, in addition to stretching, so product would have greater randomness than the reactant. So delta G is going to be greater than 0 or positive. Let's go over these questions. These will be the quick questions. How does entropy of the system change when a solid melts? Keep in mind, solid melts means it goes to liquid. So obviously its randomness is increased. And that's why it says as solid becomes liquid, randomness increases, which is S increases. What would happen if liquid vaporizes? Same thing. Vapor has a lot more freedom than liquid. The molecules in the vapor can go anywhere. So that's why entropy is also increased in case of vaporization of liquid. Solid dissolves in water. Again, when it dissolves in water, solid molecules gets everywhere, can go anywhere within that volume of water. So that means its entropy increases. When a gas liquefies, the volume is now squeezed to a smaller volume because gas fills in any volume of the container. So basically entropy decreases.